Okay, in this video, we're going to look at a characterization of T1 spaces. So let's let X be a set and say T is a topology that's on that set. Then the following three conditions are equivalent, meaning that they're all if and only ifs of each other. And we'll look at the proof that each of these are equivalent to each other as well. So the first one is that the topological space X comma T is a T1 space. And remember, T1 was some kind of a measure of how well we could separate points. So watch the video on T1 spaces that should be just before this one in the playlist. Number two, for each element of the set, that singleton is closed. And then number three, if A is any subset of X, then A should be equal to the union of all the open sets that contain A. So my notation that I'm using for that is, again, I'm taking the intersection over the following sets. So all the open sets such that A is contained in U. All right, so each of these things are equivalent to saying that the space is T1. So remember, how do you do the following are equivalent type of proof? Typically, you try to show 1 implies 2, 2 implies 3, and then 3 implies 1. So you make kind of this circle, if you could visualize that. All right, so let's take a look at the proof of 1 implies 2. So we're going to try to show if X is T1, if XT is T1, then each singleton's closed. So what would that look like? And we've got a little picture here. It's good to try to draw these out and think about how is my argument going to go to try to show that the singleton X is closed, and how's the T1 property going to come into play. And the T1 property, remember, guarantees me that if you've got two distinct points in the space, X and Y, you know that each of those points have neighborhoods of each other where X is not in the neighborhood of Y, and you can find a neighborhood of X that doesn't contain Y. I'm not saying the two neighborhoods have to be disjoint. Just remember, the one neighborhood around X has to miss Y, and the other one around Y has to miss X. And so if you think about it, if you want to show the singleton X is closed, that yellow set is the complement of X. We want to show it's open, and the idea is that that set V is a good neighborhood of Y that doesn't contain X. So let's try to put that into words. So suppose that X comma T is a T1 space, and let's let X be any element of the set X. So again, to show that the singleton X is closed, you need to show that the complement of the singleton X is open. And remember, that means that we need to ensure that it has for any point in the complement of X. So again, this is what I'm referring to as the complement of X. For any point in the complement of X, you should be able to find a neighborhood of that point that's completely contained in the complement of X. So let's let Y be any point in the complement of X. So since X comma T is a T1 space, just like in my picture, we should be able to find some neighborhood V that contains Y, but that does not contain X. So again, that's where the T1 property, the T1 hypothesis is coming into play. So what does that say though? Well, if Y is in V, but X is not in V, well, by definition, that means that V has to be a subset of the complement of X, right, since it misses X. And so what did we just show then? We just showed that X minus X has a neighborhood V of that point Y. And so we've shown that any point of the complement of X has a neighborhood that's contained in the complement of X. Therefore, the complement of X is open, and of course, conclude that X itself is closed. The singleton X is closed. So that takes care of 1 implies 2. Let's move on to 2 implies 3. Let me scroll up just so you can see what are we going to do next. So now we're going to assume that each singleton is closed, and now we're going to show that any subset is equal to the intersection of all the open sets that contain it. And so let's take a look at 2 implies 3. So suppose that X is closed for the singleton X is closed for every element X. And here's maybe our picture over here that we have. So I've drawn just a subset A, and what we're going to look at is a point that misses A. So we're going to look at a point Y that's outside of A, and then we're going to look at the yellow set is the complement of Y, and just notice, well, the complement of Y contains the blue, it contains A. So if you pick any point outside of A, the complement of that point is 1, it's open, and 2, it contains the set A. And that's the idea. So if you think about taking the intersection of all such sets, you're trying to argue to yourself that you should just get A out of that mess. So let's put some words to that. How would that look? So let's let A be any subset of X, and let's take Y to be any element of the complement of A. So just like in my picture, Y is outside of A. So by hypothesis, that singleton Y is closed, which means that its complement is open. So that's my yellow set in my picture there. And so I've got an open set that contains A. So A is contained in the complement of Y. And maybe to kind of argue not proof by picture, but how come, right? Well, it's because y was chosen so that it's not an A. So that's why A has to be contained in the complement of y. So what have we shown? We've shown that A is contained in any such set x minus y for any y that's not an A. And so if A is a subset of all such sets x minus y, if it's in every one of them, well then it's in the intersection of all of them. So I'm taking this intersection over all y's that are not elements of A of all these open sets that have that form. All right, so what do we need to do though? Maybe you notice I show that A is a subset of, the intersection of open sets that contain A. On the other hand though, I need to show that this is an equality. So what we need to do next is just show maybe the reverse inclusion. And so I'm going to fix some notation to maybe clean this up a tiny bit. Let's let capital Y be the collection of all of these subsets of x minus a single point, where that single point though is an element that's not contained in A. So let's let B be in the intersection of all of these open sets in Y. So what is this again? This is just trying to a little bit different notation as to this right here. So just restating, redescribing this set here, and I'm going to show you if B is in that, now I'm going to try to show you that B has to be in A as well, and therefore we could have an equality. So let's let B be in that intersection. By way of contradiction, what if B wasn't an element of A? Well, then A would have to be in the complement of B, but then that tells me that the complement of B is one of these sets that's in this collection Y here. And in particular then, if the complement of B is in one of these, and if little b is contained in all of these things, right? That's what it means to say little b is an element of this. Little b is in every one of them. Then little b has to be in the complement of little b, which is ridiculous. That's a contradiction. So what can we conclude there? We can conclude that the intersection of all the open sets that what did I say here? That look like x minus y, where y is not an element of A, that is contained in A, and thus they're equal. So we've shown that A is equal to the intersection of the open sets that contain it. Last thing we got to do is 3 implies 1. What was that again? We're going to suppose that we have that kind of intersection property, that A is equal to, any subset is equal to the intersection of all the open sets that contain it. Now we're going to show that that makes x comma t a T1 space. So let's do that. Sorry if I gave you a little bit of motion sickness there. So let's let x and y be 2 distinct points. Remember, the thing that we have to do is we have to come up with neighborhoods of x and y such that the neighborhood of x doesn't contain y and the neighborhood of y doesn't contain x. That's our goal. And so how are we going to use this hypothesis from 3 here? So from 3, the singleton x is equal to, well, it's equal to the intersection of, again, all the open sets that contain x. So what does that tell me? Well, there definitely exists some open set such that x is in that. But I could also ensure that for that particular open set, I can find an open set that contains x, but also that misses y. And how do I know that I can do that? How can I say this? And this is kind of subtle, but it comes from this property here, this equality. Like, what if you couldn't do that? Well, in that case, then, that would mean that when I take this intersection here, x and y would use the exact same u's in this kind of intersection representation there, right? They would have the exact same open sets here. But if these two intersections use the exact same u's, then that would force the singleton x to be the singleton y, which would contradict that x and y are distinct. So I think I wrote that out a little bit more cleanly right here. Otherwise, again, x and y have the same u as above, where I'm referring to in this kind of intersection representation, but that would force x equal to y, which we know is baloney because we assumed x and y are distinct. So therefore, you have to be able to find an open set that contains x but does not contain y. And again, that's how we're using the hypothesis for 3. So similarly, you can make the same argument for y as well. So if you look at the intersection representation of the singleton y here, you should be able to find one of these neighborhoods that contains y that doesn't contain x. Otherwise, again, these two expressions would be the exact same, which would force x equal to y, which again is not possible because we assumed x and y were distinct. So again, just to put that into words, similarly for the exact same reasons, you could find a particular open set W such that y is in W, but x is not in W. And so what have we done? We have found an open set that contains x but does not contain y, and we've also found an open set that contains y but does not contain x. And again, that is the separability criterion that defines the T1 property. So thus, x comma t is a T1 space.